Well, I want to welcome everybody to the Baskett Wildlife Research and Education Center. My name is Ben Knapp, and I'm a faculty member in the School of Natural Resources, and I study silviculture and forest management. And I'm also the superintendent of this property. So I'm going to give just a brief background on the Baskett Center, and then talk a little bit about what we do with this facility within the college. So this is one of the farms and centers within the Ag Experiment Station of the College of Agriculture, Food, and Natural Resources. The property is a little over 2,000 acres, and it's mostly forest, and it's administered and managed by the School of Natural Resources. So it's a great asset to our students. It's a living laboratory where we bring students out for a number of classes and have research projects and other hands-on experiences. Now, the history of the Baskett Center is interesting. It's tied in roots of conservation within the country. Prior to acquisition, this area was subsistence farms. And in the 1930s, with the Reclamation Administration in 1935, 17 farms were pulled together and became federal ownership. And then in 1938, in agreement with the University of Missouri, that area, previous 17 farms, became the Baskett Wildlife Research and Education Center. And in April of 1938, the dedication of the center was actually done by Aldo Leopold, who's one of the icons of conservation. So this property, it's a little bit over 2,000 acres, and it's about 20 miles from Columbia, from the campus, and so it's very accessible for students. Now, rooted in the conservation, it started off as an arboretum and a wildlife refuge with the mission of teaching and education as well. It's been managed by faculty members in the School of Natural Resources throughout much of its existence, including Thomas S. Baskett, who is the leader of the Fish and Wildlife Co-op unit, research unit that was associated with the university, and also an adjunct faculty member. And he managed the property from around the 1950s up through near 1980. And then in 1988, the property was named after Thomas Baskett as the Baskett Wildlife Research and Education Center. And so today, we use this property for a wide variety of activities with students. We do have ongoing research projects where we study forest succession, forest ecology, and forest dynamics, including a long-term set of forest monitoring plots where we take data on the way that forest is changing. We have a eddy covariance tower as part of the Ameriflux network to look at exchange between the atmosphere and the forest and look at carbon dynamics within the forest. We have a prescribed fire program where we have students come out and they can get red card certified, and we do prescribed burning, and that's built into a research design, but is also done operationally with our students and our student fire organization. Parts of the area we're actively managing for timber and practicing forest management to improve the health of the forest. There's a long history here of wildlife research, including quail, grouse, and more recently doves and mammals as well. And so this site is just really critical for the School of Natural Resources, for our courses, for our students. Every year we have over 12 classes, a dozen courses come out and use the site in different ways. So we're very happy to have this field tour to look at some of the soils and talk about some of the ongoing work in terms of soil classification and soil science. So welcome, and I hope you enjoy this virtual tour of the Baskett Center.
Good morning. I'm Mark Abney with the Natural Resources Conservation Service. I'm the Assistant State Soil Scientist here in Missouri, and we are standing right next to Soil Pit 1A, and we're on a summit position on an upland ridgetop. We're on a 3% slope here. These ridgetops are very narrow, and we're not too far from the Missouri River, so we have some loess deposits here. The loess deposits are the Peorian loess on top, and then the Roxana loess is below that. And then if you go deep enough, we're going to hit some Mississippi residuum geology. The depth to water table in this soil pit's about 42 centimeters. The soils on these ridges through here were mapped Weller, and also a soil called Marion. And if we put them in sequence, the Weller and the Marion soils are classified as aquatic chromic haplodauphs. They're both, the Marion is somewhat poorly drained, and the Weller is moderately well drained. They both have higher water tables in them, and they are the difference between the two, Marion would have an abrupt textural change just below the E horizon. Then if you get a little drier, you would come along the Winfield soils. The Winfields are oxyaquatic haplodauphs, and they're moderately well drained and less. And then better drained yet, the well drained soils would be the Minfro soils, which is the Missouri state soil. Winfield and Minfro are both fine silty in the control section. And so we can see at this site here that we've got a deep loess deposit, and we'll be able to see in the soil pit in just a minute the soil properties and the characterization of this soil that points to them loess deposits. So that's what I have for the site information on site 1A. The top here, top 8 centimeters, is an A horizon, and it is silt loam. It's running about 15% clay. The color is a Tin-Wire 3-2 with some mixings of Tin-Wire 5-4 in there. The structure is weak, fine, subangular blocky. There's a few fine and to coarse roots. There's a very fine and coarse tubular pores in this horizon. And there's some interstitial pores in there also. The next horizon is a BE horizon. And a lot of times these horizons are mixed a little bit from tree throws. And so we get a lot of these BE horizons or EB horizons. It's 10 centimeters thick. It goes from 8 to 18. It is silt loam in texture, 17% clay. It's a weak, fine, subangular blocky structure. And it's very fine to very coarse roots with very fine and medium tubular pores and a few fine interstitial pores. The next horizon is where the argillic begins, and we've called that the BT1 horizon. It is from 18 to 42 centimeters. It's a silt loam. It's 22% clay. It's a moderate fine subangular blocky structure. There's clay films on the faces of PEDs. There's some silt coats in this horizon, a few. And it has very fine to coarse roots and very fine to coarse tubular pores and a few interstitial pores. The next horizon is this little horizon here. It's the BT2 horizon, and it's 13 centimeters thick. It's where the lithologic discontinuity is. This is the base of the Peorian loess, and it's a silt loam. It's 22% clay. It's a moderate fine subangular blocky structure. There's a few faint clay films on faces of PEDs. It has a lot more silt coats in it because of the lithologic discontinuity is perching some water there. There's a few very fine to coarse roots in this horizon, and there's a few very fine to coarse tubular pores in this horizon. You can see the color change here from the Peorian loess over top of the Roxana loess. So here's where we put our 2 on here, and we have our lithologic discontinuity. This is a 2BT3 horizon here. The 2BT3 horizon is 31 centimeters thick, the upper part of it. It's a silty clay. It's 45% clay, so we have an abrupt textural change right here also in the loess deposits. It's a moderately fine prismatic parting structure parting to a fine angular blocky structure. So we see some shrink swell properties in this horizon from the high clay content. There's common distinct clay films on faces of PEDs. There's few very fine to coarse roots in this horizon, and there's a few fine and medium tubular pores in this horizon. The next horizon is the final horizon we're going to talk about, and it's 54 centimeters thick. It's a silty clay. It's 41% clay. It's also developed in this Roxana loess. It's a moderate fine prismatic structure parting to a moderate fine subangular blocky structure. So the slight decrease in clay has also decreased the shrink swell properties slightly. There's a common distinct clay films in this horizon on faces of PEDs. The roots are a few fine to coarse in size, and there's a few fine and few medium tubular pores in this horizon. This soil here is not real characteristic of Weller because Weller should be a little better drained than this, and the high clay content comes up a little bit too high. The soil, it fits Weller better than any other soil that we have out here. The other soil would be Marion, which would have the clay way up here. So it's kind of in between, but it's a pretty good Weller site all in all, and it really shows the good loess deposits and the lithologic discontinuity between them. So we'll look at some soil structure here in this third horizon, and as I go in there and pull that out, it comes out in my hand. And structures, the structure is how the PEDs break apart, the natural aggregates in the soil. And you can see these natural aggregates are breaking into a fine subangular blocky structure. And then when we get on down into the heavier clays, we notice when we pull that structure out, it's going to come out in a prism, a larger structure. And these are nice prisms. They're moderate medium prisms. And then they'll break on down into the angular blocky structure that we described from the heavy shrink swell of the clay content in there. And you can see the angles on these PEDs that are in there. You can also see the redoxomorphic features, the gray mottles in here from the water that's the water table in here. And so lack of oxygen in the soil due to saturation causing the redoxomorphic features. And so this has a really good strong structure. And it breaks into these angular blocks, the corners on them. Okay, I just wanted to point out this lithologic discontinuity in here, and you can see the white silk coats in this layer where them two less deposits come together, and it's retarding water right there. So water is moving down through the profile until it hits this Roxana loess, and then it's perching the water right in this zone right here above that Roxana loess. And then the clay content increases here, so that also is perching water. But anytime you have a lithologic discontinuity, a lot of times you'll get that water retardation in the soil profile.
Good morning. I'm Doug Wallace. I'm an ecologist with NRCS here in Missouri. And my cohort here
is John Cabrick with the Northern Research Station, U.S. Forest Service. I'm located in Columbia, Missouri.
A couple of things we're going to do here. We're going to talk about the ecological sites that are associated with the the soil map PIPs that Mark has just described. And we're going to talk a little bit about the past history of the site, current conditions, and maybe some future actions that need to take place to keep track and remedy environmental conditions that are changing in this area. So I'd like to start out with just letting you know what our ecological classification for the site is. Ecologically, we classify this as a deep, lush upland woodland. Historically, in pre-settlement times, white oak, black oak, and post oak dominated these sites. They had a fairly open mid-story and a dense ground cover. Now, we use woodland as a technical term. A definition for woodland is different from forest in that woodlands generally have a more open crown. They generally lack a mid-story or have a very less dense mid-story, and they have a very abundant, dense ground cover of shrubs, grasses, and forbs. So, these woodland sites typically had some type of a fire history. Fire studies show that likely in this area we had wildfires that came through this area periodically on a 5 to 10 year basis. Those fire frequencies helped destroy some of the litter. They also helped stimulate the growth in grasses in the understory to keep that lush ground cover that was associated with these woodlands. So typically in the understory on a reference site similar to this, we'd have shrubs like fragrant sumac, New Jersey tea. Some of the forbs that would be associated with it would be your goldenrods, your bee balms, your coneflowers, compass plant even. And the grasses, some of the more typical and common ones were little blue stem, big blue stem, and wild rise, along with a number of other ones. Now this particular site, in the past, it has been relatively, since the university took it over, it's been relatively undisturbed for at least 80 years. So there's been little activity on these sites due to natural disturbances that may have been present prior to acquisition. Prior to acquisition, indiscriminate wildfires were set by a lot of the producers in this area to help clear out the understory and make it more conducive to grazing, which was also a common disturbance factor in this area. So that's basically the historic and the current and the past settings for this particular site.
Okay, so as Doug mentioned, this is historically a woodland site, and Doug made that link between various kinds of disturbances like fire or grazing or wind events that are really important for keeping a woodland a woodland. Without those disturbances, there are changes that take place that give the structure of this woodland more one that looks similar to a forest structure. And so one of the things that's happened here, Mark described the soils that were here. He talked about the deep loess. That loess has a high water holding capacity, so a great capacity to supply water to plants and trees. It has a very high nutrient supply capacity. And as a consequence of not having disturbances for a long period of time on those kinds of soils, we've developed a mid-story layer that's very dense in this woodland. And you can see what species that are here. We have lots of sugar maple, which is a species that requires lots of base cations and high water supply to grow very well, and it's becoming one of the most dominant mid-story plants in this woodland. And one thing about sugar maple, it has a very dense canopy, and so it intercepts a lot of the light that ordinarily would be reaching the floor of this woodland. And so if you look on the forest floor of this woodland, you'll see that there are very few plants that are visible now. We have many of our woodland indicator species, like this one here, like this bedstraw, or some of these desmodiums, but they're very diminished in size, they're very small, and they're not getting very much light. And also what's noticeable in this woodland today is that we don't have a lot of oak seedlings or other tree seedlings in the understory. And those oak seedlings that are there present in the woodland are very important for regenerating that woodland in the future. So when we don't see a nice accumulation of those oak seedlings in the understory, from a forestry standpoint, we get a little bit concerned about what the future regeneration might look like in that woodland. In contrast, that we'll say, where we do have some openings that have been created in this woodland, you can just look over there and see there's a very dense ground flora layer that has developed as a consequence of that light reaching that woodland. So some big differences in the light levels reaching the woodland floor, and big differences in the plant structure that are occurring in this woodland today. So the species that we currently see here today, we have probably the most abundant species that we see in the overstory is white oak. We have a little bit of northern red oak, and occasionally you'll see some black oak. We do have post oak in this site, which is characteristic for this kind of woodland, the D+ upland woodlands. There are a few individuals that are quite large here in this site as well. In the mid-story, we have lots of sugar maple, but we also have some hickories that are coming in places, especially as we move to some of the different soils.
And one of the common shrubs in a typical woodland is fragrant sumac. It has leaves that look like poison ivy, but it's not. One of the characteristics of the plant, it has its name fragrant sumac. If you break the leaf apart, it has a very strong odor, which is easy to identify the plant that way. But overall, this particular site as it currently stands is a good representation of what we expected to have seen here in the early 1800s, minus the sugar maple understory. The trees are excellent sized. Some of these we measured earlier, they're 25 and 26 inches in diameter, which means they're quite old, even though this is a very, very good site. It takes a long time for oaks in this area to get that large. And also the upper crowns of some of the white oak trees in the canopy are definitely show characteristics of being a lot more open in the past. So we know that we can come in here and maybe do some site work and bring this site back to original reference conditions if we need to or if we want to.
So we should talk a little bit about the future of this stand. So one of the things that we're concerned about is we mentioned the lack of advanced reproduction. So we're concerned about what species that we might want to have here in the future if we need to regenerate these trees. And as Doug mentioned, if we restore some of those disturbance processes, that will remove some of that mid-story, allow more light to reach the forest floor, and over time we'll probably start to accumulate more oak seedlings, as well as develop a richer ground flora layer that's an indication of this woodland condition. These woodland plants are present, but they just need more light to express themselves a little more fully. In the long term, we also think about climate change and what that might mean for a woodland like this. And there's a lot of climate models and projections that are predicting what the future might be like. It might be a little warmer, especially in our wintertime. We probably are going to get more rainfall. But what's most common among all projections of future climate is there's expected to be more variation in our climate. So extended droughts, extended periods of heavy rainfall along with excessive rainfall. That variation is probably very important. And the soils on this site with that D+ are very, very well buffered against some of those changes. So this is a place in the landscape where if a drought occurs, these soils have a capacity to supply water for a very long period of time during that drought period. So we'd probably be able to retain a lot of plants that might ordinarily succumb to drought if that soil didn't have that water holding capacity. Similarly, these sites also have a very high nutrient supply capacity, and that allows species that are very demanding for base cations like calcium and magnesium to persist well in this landscape as well. So from a management standpoint, if we're trying to think about how to manage this stand to position it well for an uncertain climate, this is a place where we have some ability to have a little more species diversity. We could probably include our management for species that are a little more sensitive to drought because these soils will help us get through some of those dry periods.
If we go ahead and open up the understory and even maybe open up the overstory a little bit, that allows less competition. And when we do hit these extreme events, especially the drought cycles, that'll allow the trees that remain to be able to compete and hold onto the site. We see across Missouri where we've got really dense stands that if we've got a heavy competition and a drought cycle comes in, we lose a lot of the trees. Mother Nature picks those trees. If we want to kind of mimic that, but be able to pick the trees we want to leave in the stand, then that's why coming in with some kind of active management in the understory and overstory will help perpetuate these stands and also allow them to be more resilient to different climatic events.
That's right. Through our management, we can make the stand more resilient, and with our knowledge of how that soil influences the ecological function here, we can tailor that management to really fit this site very well.
Hey, it's me again, Mark Abney, Assistant State Soil Scientist for Missouri, and we've just walked down slope from Site 1A to Site 2. We've moved west down the slope. We're standing on an upper shoulder position. This upper shoulder position is on a 15% slope. It's west facing. So we're, like Doug and them are going to talk about, we're on an exposed back slope, the upper part of a back slope. Just below me, we drop off the shoulder into the steeper part of the back slope, and then this will go down to Site 3 where this benches out. And so here we see a lot more rocks. The Mississippian geology is exposed here, and the soil is residual from that Mississippian geology, and I just have a couple rocks here in my hand. I had to hunt hard to find them, but I got two, and I just wanted you to notice some things about these rocks. Is they're rounded, which means they've moved down slope a long ways. It's knocked the edges off of them. So the materials that are on top of this, down to almost 35 centimeters, are colluvial materials that have moved down slope over top of the old residual soil. So we have another lithologic discontinuity here. And this soil here is Bardley-like soil. I always say like because we rarely find a soil that fits exactly in the central concept of the series, but that's why the series has a range of characteristics, because if we was going to map this, we would map this soil Bardley. Bardley's a very fine typic haplodaup. It's moderately deep to limestone bedrock, and it's a well-drained soil. Just above the lithic contact, we're starting to see the water being slowed down enough to drop out some redoxomorphic features. We get a lot of runoff here due to heavy clays. The soil will get saturated in that upper part of the lithologic discontinuity, and then once it's saturated, we have like 100% runoff because it moves into the clay very slowly. That's pretty much it on the site information, and so we'll head into the pit now and look at the pet-on description. This site here is a Bardley soil, and we see colluvial material over the top of residual material. And this residual material is nice and red clay, and this colluvial material is darkened and full of coarse fragments. Just wanted to say again about the coarse fragments. Notice they're nice and round. They've moved a long ways down slope. And this material has been deposited over this truncated residual soil. And it was probably truncated in a interglacial retreat. A lot of erosion took place, and then the lust blew, and colluvial materials moved down slope with the lust. So there are hill slope sediments in here also. That's colluvial material also, but it's fine earth fraction. So we talk about it a little bit different. But all of these coarse fragments in the surface are well rounded. When you get down the subsoil, the coarse fragments have more edges on them because they weathered in place. So that's one way we tell about fragments and how they move. This particular piece of fragment is triplytic chert. We find triplytic chert's kind of rotten chert. It's weathered out, a lot of the material in the chert, and it becomes lightweight. It's kind of a rotten type chert, and it's a lot of times it's white like this. And so triplytic chert in the Mississippian geology, we find it a lot. And this is Mississippian geology from our site information. And so we're going to go down through the pet-on here. This is an A horizon. This A horizon has a nice structure. It's got a weak fine subangular blocky structure, and you can see the blocks coming out there. It probably parts to a weak granular structure, but the blocks are more prominent, so we put the blocks in. It's a silt loam with running about 15% clay. It's not molic colors, it's ochric epipedon, and the coarse fragments in there are about 25% gravel and about 5% cobbles. It's got very fine to coarse roots throughout, and it also has very fine and fine tubular and interstitial pores in it. That's an A horizon. This, once again, we're calling this a BE horizon. These horizons get mixed once again from tree throws, and the amount of tree throws that occur on this soil over time is tremendous mixing of the soil. And so trees root down into the subsoil, and then whenever they're blown over with the tree throw, they flip up some of the subsoil into this E horizon, and they end up having both B materials and E materials together in that horizon. We call them BEs or EBs, depending on which material there's more of. So this is a BE horizon. It actually picks up in texture and clay content a little bit because of the mixing of the B up in it. You can see a lot of silt coats in this, which is typical of an E horizon. And this was running about 20% clay, so the increase was about 5%. And it's about 15% sand. It's got about 45% fragments in it. 35 of them are gravel and 10% cobbles. And we can see, we can pull these cobbles out, and they're well rounded. They don't have a lot of edges on them. And you can see the nice contact of the truncated soil here where the red clay starts and the colluvial materials end. Then this red clay is once again residual material. This next horizon is a 2 BT1, and it picked up in clay a lot. It went to 55% clay. It's got it will have a prismatic structure to it. You can pull that structure out and break out the prisms. There's nice moderate medium prismatic structure. That breaks down to moderate medium subangular blocky. Once again, I think I said the clay content on that was about 50%, 55% clay, 10% sand. The coarse fragments dropped off a lot because these are residual material coarse fragments, and so we went down to 5% gravel and 1% cobbles, a total of 6% coarse frags. There's clay films on all the faces of PEDs. About 40% of the PEDs are covered with clay films. 5% of 6-2 in root channels, so it's starting to slow the water down as the water moves down through this profile. The heavy clays are swelling, and they're slowing that water down and dropping out some redoxomorphic features in the root channels. There are very fine to coarse roots throughout that horizon, and there are very fine and fine tubular and some interstitial pores in that horizon. Brings us down to the next horizon. That's a 2BT2 horizon, and it's 20 centimeters thick. It has 45% clay and 35% sand, so the sand is increasing a lot in this horizon. Once again, our structure, when we pull that out, we got enough clay and in that we're going to have prisms, and so we're pulling out prisms in that, and that parts to a moderate medium subangular blocky structure. And we see some coloring from the limestone that's weathering out in that horizon. Not as much in the one as in the one below it, which will be that next horizon that's called a BCR. So you can see these boundaries are irregular once we get down closer to the rock. Over here we have a nice solid piece of limestone that's not weathered. And I just wanted to point that out because underneath this soil there are varying depths depending on the limestone material. So you can go from something that's maybe 25, 30 inches to limestone to something that would be 40, 50 inches to limestone in this same soil because it's going to vary across as you go across the soil type. So that is our 2BT2 horizon. It has a moderate medium prismatic once again, and it's 30% clay films on the faces of PEDs in that horizon. It's very fine to medium roots throughout, and very fine and fine tubular pores and a few interstitial pores in that. That brings us to the next horizon, which is a 2BCR. So we have B material mixed with CR material, and CR material is weathered bedrock. And so this white material in here is weathered out limestone. Don't really have a structure, it just kind of falls out. It's got a lot of sand in it, and it also in this horizon you can see B material down in here in places where it's weathered out and weathered into clay, and that it has structure in this B material. So this has a really irregular boundary depending on the weathering that took place. And there's manganese stains in this horizon because it's slowing that water down, and there's also some redoxomorphic features of reduced iron in gray mottles in that horizon. It's 33 centimeters thick, and then we hit an R horizon. The R horizon is at 114 centimeters, and it's limestone bedrock, and it's pretty solid stuff. It's so this is the bedrock that's underneath, and this is probably the average depth of this soil is like this right here, this profile. It's got a lot of limestone available for these plants, and I'm sure Doug and John are going to talk about the limestone loving plants that are on this site. So that's really all I have for this PED-on, and we'll field any questions at break time. Thanks.
All right, well, we've moved on to the second site. We've moved downslope. Mark has shown the group that this soil pit is much different than the one on the upper slopes that we looked at. And we can also see a similar switch in vegetation due to that. Historically, this was ecologically classified as a chert limestone backslope woodland. So we discussed previously that woodlands are generally more open than their forest counterparts. There's a lack of a midstory and a dense understory. On this particular site, since it's a little drouthier, we would expect a little more drier species to have been present in the past, with the crowns maybe a little more open than the upland site that we looked at. So this probably had the same burn cycle as our previous site had. So every 5 to 10 years we had a wildfire that would come through here, and again take care of some of the litter and help stimulate the grasses and forbs to keep that understory nice and dense. And past on this site, since again this is similar to the upland one we looked at, this has had no disturbance on it, or very little disturbance for the last 80 years. So from a standpoint other than prior to acquisition, we still probably had grazing on this site. We probably still had those wildfires. But those basically stopped 80 plus years ago. So because of that, we've had some changes in composition from the historic conditions that were here. And John's going to talk about what we have currently on the site.
So currently, if we do look at the overstory, we have a lot of the same species as we saw in the site just up the hill, about 200 feet away from us. So we had a lot of white oak, we have some black oak, occasionally you might find some northern red oak. Post oak is present on this site. In the mid-story we have a lot of sugar maple, and we also have some cedar that's coming into this site as well. But there are some big differences that we can see in the structure and also in the current composition that are related to the soil properties themselves. As Mark mentioned, we have a lot of coarse fragments in the soil. The soil is shallower. We have clayey textures in the subsoil, which supply less water So that droughtiness that Doug mentioned shows up even in the undisturbed woodland condition today. If you pan around and look, you'll see that the understory here is much denser here than it is just up the hill, that with the same site history because of the soil differences, because of the dryness of the soil, the lower water holding capacity. Something else that we see in this ecological site is that we have the ability to accumulate oak seedlings in the understory, unlike where we were at the last site. We have more light that's reaching the ground. The sugar maple that's in the midstory is smaller in diameter, is probably fewer in number than up the slope. And so that's allowing more light to reach the woodland floor, and it's allowing seedlings of oak to accumulate and become large. So because of the edaphic conditions, the site conditions provided by the soil, we have some different outcomes that are occurring that are largely a function of that soil and site as opposed to the disturbance frequency.
I would also add that one of the other driving factors on this site is that we're on a back slope, and this back slope has an exposed or a southern and western exposure, which because of that condition, the sunlight stays in this area longer than we would on the more protected slopes. So that adds another element to the droughthiness of the site, along with the more shallower soil and the rocky profile.
So we like to think about what the future of this woodland might be. This has excellent potential for restoration. So if we were to do some thinning in here to remove some of that midstory, apply some prescribed fire, we would probably get an excellent response from the ground flora. In terms of a future climate, with that uncertainty that we described at the first site, if we manage this site for that woodland condition, we're probably going to ensure that it's very well positioned for that uncertain climate and for extended droughts, especially, as Doug mentioned before, if we can favor those species that we know are best adapted to the dryness of this soil. And so part of our management will, if we were able to do that, that would give this soil or give this forest, this woodland, some buffering capacity to some droughts or things like that that would occur under a future climate.
One other thing, if we do come in and do some restoration work in here, we should see an excellent response with the understory, especially if we can bring prescribed fire into the system. We do have patches here where we have a fairly typical historic conditions of the understory, where we've got the native grasses still there and then the native forbs. And so generally on sites like these, especially these exposed sites, a lot of the original ground flora is still present, either as small plants or even in the seed base. So if we open up these sites, run fire through it, these sites generally almost explode with a profusion of flowers and grasses that were historically here in the first place.
Well, welcome to Site 3, and we've moved down the slope, down the back slope to the west, and now we've benched out on a finger. So these are structural benches. They're on Mississippian limestone geology, and they're holding these benches up. And we'll see in the soil in just a minute that there's some loess still on these soils because the slope decreased and these old fingers held some loess on them. The slope here is 14%. The stratigraphy is silty and clayey loess over hill slope sediments, colluvial materials. The geology is Mississippian. The hydrology is moderately well drained, and the soil is probably roachport-like soil. Roachport's an oxyaquic haplodalph. It's fine silty. It's moderately well drained, and the loess deposition is probably around 15 to 40 inches in the range for that series. It's a deep soil. Its counterpart is Bonfim soil. Bonfim soil is a lot less loess and is shallower. It's only moderately deep, 20 to 40 inches to limestone bedrock, and it's a typic haplodalph, and it's well drained. So that's the two soils that would occur in this position. When you get in on the steeper side slopes and back slopes, we would have a soil like Klinkenbeard, which is skeletal, and a Zamalisol. So them soils are on the really steep side slopes of this area. So this is what we have for this site information, and now we'll go look at the soil in the pit. Well, welcome to the soil pit on Site 3, and this pit is a nice lust deposit on this structural bench, as we talked about in the site information. It has an A horizon right here, and it's 6 centimeters thick. It's a silt loam, has about 16% clay and 5% sand. It's got a weak, fine subangular blocky structure. You can see that structure come out of there, and you can see the little blocks in there. It has very fine to coarse roots throughout, and it has very fine to medium tubular pores and fine interstitial pores throughout. This next horizon is a BE horizon. Once again, we have mixing of the B and the E due to disturbance from tree throws. And so this is the BE horizon, and it's 8 centimeters thick also. It's a silt loam. It's 18% clay with 5% sand. And we pull that structure out of there and look at it, and once again we have a nice subangular blocky structure in there. The next horizon is a BT1 horizon. It's 15 centimeters thick right here, and it's a silty clay loam with 39% clay and 3% sand. It's got a prismatic structure, so when we pull this structure out of there, we can see the prisms coming out of the face, and these prisms will break down into this nice blocky structure, and it's a good moderate to strong structure in that horizon there. You can see the structure really well. It has 30% clay films in this horizon. It's got some silk coats, about 1% silk coats due to stripping. It's very fine to medium roots throughout, and very fine to medium tubular pores and fine interstitial pores throughout. This is a BT2 horizon. It's 11 centimeters thick right here, and it's 45% clay and 3% sand. So the clay continues to pick up in the argillic horizon. The argillic would start here, go down this way, and it's got the nice clay bulge in it. And so we have this BT2 horizon. It's got weak, fine prismatic parting to a moderate fine subangular blocky. And so we pull out, once again, we can pull them prisms out of that. You can see the prisms coming out, and then they're breaking into these nice, moderate, fine subangular blocks. Nice structure. It has 2% silk coats in it, and it is very fine to coarse roots throughout, and very fine to medium tubular pores and fine interstitial pores. Next horizon is a BT3 horizon, and it's right here. This horizon is 26 centimeters thick. It's a silty clay. It has 42% clay and 3% sand. It's a moderate fine prismatic parting to a moderate fine subangular blocky. So we can pull these prisms out of the soil, and these prisms come out, and then they break into nice blocks. You can see the blocks. Good moderate structure. It has 40% clay films on faces of PEDs throughout, and it has 5% silk coats due to stripping, and very fine to very coarse roots throughout, and very fine to medium tubular pores and fine interstitial pores throughout. The next horizon is where the lithologic discontinuity is. Once again, we have the two lust deposits. We have the Peorian over the Roxana loess. This is the lithologic discontinuity here. And so we go to a 2BT4, and the 2BT4 horizon is moderate fine subangular blocky structure. So we lost the prisms. It's a little firmer than the one above it, and the color, you can see the color change in it. It's a little more reds in it, and the texture dropped back in clay to 39% clay. It's a silty clay loam. It has 1% chert gravel in it, so There's some flecks of chert in it. It's a moderate fine subangular blocky structure. There's 60% clay films in this horizon. On faces of PEDs, there's 5% silk coats, and it's got very fine to coarse roots throughout. The next horizon is a 2BT5 horizon. The 2BT5 horizon is 30 centimeters thick. It is a silty clay loam with 38% clay and 5% sand. It has 1% chert gravel in it. And there are 40% clay films on faces of PEDs throughout. The structure is moderate medium prismatic, parting to moderate fine subangular blocky. So we ought to be able to pull some prisms out of there. Comes a nice prism. You can see that. Here you can see some nice manganese stains. The black stains there is manganese. So it's slowing the water down and dropping out precipitating manganese as the water slows down. So the manganese falls out, and then this structure breaks down into a nice fine subangular blocky structure. You can see these blocks coming out here. It has 10% silk coats and 40% clay films on faces of PEDs. It has very fine to medium roots throughout and very fine to medium tubular pores throughout. The last horizon that we show here, this soil was a lot deeper when we dug it, but for safety reasons we filled it back in. And so the last horizon we're going to look at is a 2BT6 horizon, and it's 29 centimeters thick, and it's a silty clay loam with 38% clay and 5% sand with 2% chert gravels. It's a moderate medium prismatic structure, and it parts to a moderate fine subangular blocky. So we can go down here and pull out these prisms. Some nice prisms coming out, and break that down into that finer structure that we mentioned. It's got nice structure. It has 20% clay films on faces of PEDs, 10% silk coats, and very fine and fine roots throughout, and very fine and medium tubular pores throughout. So that pretty much sums up this PED-ON. This is Site 3. We're on a structural bench on the Mississippi in geology. Thank you.
All right, Mark has just finished up the information on the soil pit that we have here. And Mark mentioned that there was some benching going on here that may have influenced the site. That, along with the lower slope position, we're about 2/3 down from the summit areas. And the surface lust that Mark talked about with the lack of gravels, fairly decent profile. And finally, the water accumulation we're getting from upslope positions really contributes on this site to a more mesic condition. Now, we're technically on an exposed site, but with those issues that I mentioned, plus the type of vegetation we hear, it's really looking more like a protected type of community. So the ecological classification for this site would probably be a loamy protected backslope forest. The reference community was dominated by an overstory of white oak, northern red oak, and occasional black oak. The canopy was tall and closed. It would have had a mid-story present on the site. What's different from these first two sites that we looked at, the ground cover here was dominated by spring ephemerals, woodland type of grasses, and even ferns, compared to the upper two sites where we had a ground flora that was dominated by prairie species, both forbs and grasses. Fire likely played a minor role on this site. We're 2/3 down the slope, and so the fire frequency probably was anywhere from 10 to 25 years. But even more importantly, if we even did get fire down in this area, it was a low intensity fire, so we didn't have the impact of fire like we did on the other two sites. These longer disturbance periods allowed a lot of shade adapted species to be maintained and exist on these sites. The past history is fairly similar to our upper two sites that we looked at. We probably had some uncontrolled domestic grazing. We probably had some wildfire fires, but they were also of lower intensity. And even with the grazing, we did not have a fairly dominant ground flora here that the cattle would have stayed in and browsed for any length of time. And they probably would have just passed through from the upper sites, which had better grazing forage, down to the bottomland site we're going to view next, where we actually had some water present where they could have used. So since the late 1930s, this site has been relatively undisturbed, which leads us to the current condition for John to talk about.
So currently on this site is dominated by the species white oak, but it's also common in this position in the landscape to find northern red oak, sometimes black oak, and even occasionally post oak. Sugar maple is a very common species in this position. As you can see, looking in the site, there's lots of sugar maple in the mid-story, but this is a position because of where water is able to move into this landscape position that we can actually grow some large diameter sugar maple so it can become a component of the overstory in some locations on this kind of site. Doug mentioned a lot of other shade tolerant species that can accumulate in here, and so we have flowering dogwood we'll show you, and we also have ironwood, a hop hornbeam, that's becoming more common and becoming more abundant in this slope position. So one thing that I wanted to point out about this site is that we mentioned the woodland condition a little farther up slope, like at site number 2 and also site number 1. But when we get in these lower slope positions like this, if you'll look around, you'll notice that we have a high density of trees. The trees are a little closer together, as well as being very, very large, which is a little more characteristic of that richer site condition, that higher density that projects a little more of a forest structure to the vegetation, meaning that we have an overstory, a midstory, and an understory, unlike that woodland condition. But it's largely because of this slope position and location relative to the flow of water in this landscape. In terms of the future of this site, this is a very rich site. It has the capacity to maintain a lot of species diversity. So even under various climate scenarios where we can have extreme events, extreme droughts, extreme wet periods, this is probably a position in the landscape and with a soil that lends itself to a high water holding capacity, a high ability to supply water even during periods of drought. And so these are places that we can probably maintain our species diversity from a management standpoint. We'd probably want to manage this forest here as a forest rather than a woodland. Fire would be a tool that we might use on occasion, but it's probably not a tool that we'd use with great frequency like we would on a woodland site. The other thing to note, if we look at the understory, if we're interested in oak regeneration and perpetuating these oaks like we have in the overstory, this is going to be a site that's going to be a little more challenging to do that. It will probably take more planned management, more thoughtful silviculture to make that happen. And it's largely because in these rich site conditions like this, that we have an inability to accumulate oak advanced reproduction, those large seedlings of oak in the ground flora and the ground layer that are so needed for regenerating oaks. Oaks are disturbance survivors. They spend a lot of their carbohydrate that they develop early on developing root system. And until they develop a big root system, they can't grow or be released by a timber harvest. And so these are places where deliberate effort would be needed to establish that oak advanced regeneration through some thinning operations that we might do to allow a little more light to reach the forest floor here to help that oak grow.
Well, John mentioned earlier, and Mark mentioned it, that this is really a productive site. So it's got a capacity to react better to droughts, long-term droughts, because we have a lust cap on this, and we also have a fairly deep soil profile. It's almost pure loams, and so it has a really good water holding capacity. So if we do hit extreme droughts, we've got internal soil moisture that might keep this community intact and keep it from changing dramatically over time.
Well, welcome. We're at Site 4. We've made it to the bottom of the hill. We've moved west and come down off of a steep back slope above us. And you're looking west. We're down in the bottom. We're on a floodplain step. And we're going to see in this soil that we have some alluvial materials down here. So the landform position's a floodplain step. Oh, we're on Site 4, if I did mention that, Site 4. We're on a 2% slope. The stream is just below us. The stratigraphy is loamy alluvium over gravelly alluvium over silty alluvium. So there's several alluvial deposits here. The geology is, of course, Mississippian, just like the other sites. The hydrology is about to happen. If you can hear the thunder in the background, we're about to get some serious hydrology here. So we don't want to wait around to see what kind of soil hydrology is going to go on here after this event happens, so we're going to hurry through this. The soil is it's not a good dameron. A dameron is a cumulocapadol, but it's probably as close to a dameron as anything. And dameron's a well-drained cumulocapadol. It's very deep. The other soil that's mapped in this position is a Jemerson soil. Jemerson's fine silty. It's a typic haplodolph, and it has an argillic horizon in it. There's one other soil that's not mapped in this area that's a possibility, is a soil called woolly. Woolly's a loamy skeletal cumulic haplodol, and it's well drained and it's deep. So that's the site information, so let's go into the pit. So we've moved down into the pit now, and we're going to talk about the soil properties. This is an A horizon right here. Notice the dark colors on here. We think it's a mollisol. We don't have the lab data back, but pretty sure this is going to be a mollisol. Don't have an argillic. It's got too much stratification, but it does have mollic properties, and I'm sure the base saturation's up there pretty good. The surface is a silt loam. It has 20% clay. It's a 10YR32 color. It's a moderate fine subangular blocky parting to moderate fine granular. So we can pull that structure out and see the blocks and part the blocks to a nice granular structure. Looks like a oat bran cereal, granular structure. So then it has very fine to very coarse roots throughout. It has very fine to coarse tubular pores throughout, and many fine interstitial pores throughout. The next horizon is a BW1, and it's a strata just below the surface, and it's 22 centimeters thick right here. It is a loam texture. It's 25% clay and 30% sand. We pull that material out and look at the structure. It parts to a nice subangular blocky structure. It has many very fine to coarse roots throughout. It has very fine to coarse tubular pores throughout, and many interstitial pores. The next horizon is a 2BW2. It's 27%, 27 centimeters thick right here. It has 60% chert and limestone gravel and 5% chert and limestone cobbles. They're sub-rounded, rounded, and very well rounded due to being in an alluvial situation. It has a weak fine subangular blocky structure. It has very fine to medium roots throughout, very fine to medium tubular pores. We can look at that structure real quick. You can see a lot of coarse fragments in it. They're well rounded. They've been in the creek a long time. Nice rounded creek stones. And that structure coming out of there is a nice fine subangular blocky structure. The next horizon is a 2BW3 horizon. It's 17 centimeters thick right here. And it's a loam texture. It's 26% clay and 40% sand. It has 65% chert and limestone gravel. They're rounded, sub-rounded, and a few subangular pieces in there. So some of it's been in the creek a long time. Some of it's recently just moved down slope as colluvium and been deposited here with the alluvial materials. 65% coarse fragments in that layer. It has a weak fine subangular blocky structure. It is very fine to medium roots throughout and very fine to medium tubular pores throughout. The next horizon is a 3BW4 horizon. Could be an Old Buried A horizon. It's 15 centimeters thick and it's right here. It is silt loam. It's 18% clay. Has 2% chert and limestone gravel in it. It's moderate fine subangular blocky structure with silt coats. It's very fine, has very fine to medium roots throughout. Has very fine to medium tubular pores throughout. The last horizon is a 3BW5 horizon. It's 34 centimeters thick and it's down here. It's a silt loam, it's 22% clay. It's a gray with brownish iron oxide masses, has redoxomorphic features in it. It's 3% chert and limestone gravel in it. And that pretty much concludes the soils on this site. The hydrology is coming down, and so I think we're going to head for high ground. Have a great day.
Good morning. We're going to talk about the veg on this site here. Just want to point out a little something that you may have picked up on already, is that when Mark was giving his presentation, it was a little damp. Today it's very dry and nice and cool, so we actually moved to a different day to finish the filming, so good morning on that. So this particular site is a really interesting community. We would probably classify this as a loamy, gravelly, upland drainageway forest. And that's because most of these sites, or almost all of them, are associated with first and second order streams. So we've got fairly narrow corridors here that the community is working with. Historically, stream dynamics, the productivity of the soil, Mark mentioned how productive these were, and the close association with the uplands here allowed a rich variety of species to exist on this site. Historically, the reference community was a forest with a combination, this is kind of unique because of these sites, of bottomland and upland species. So some of the typical canopy trees were sycamore, black walnut, hackberry, northern red oak, sugar maples, ashes, elm. So we had a rich variety here. We also had a very dominant mid-story where we had Ohio buckeye, pawpaw, blue beech, and a really rich ground flora. So we're way down on the landscape. Wildfires had little to no influence down here. What really played a role on this site were the local stream dynamics. These streams are ephemeral, and during most summers they dry up except for isolated pools that are shallow and scattered through the drainage way. We've had recent rains in the area, so our stream corridor is pretty active with a flow actually going on here. But in normal years, this time of the year, the stream corridors would be primarily dry. Because they were high gradient streams, these drainage ways were flashy. In other words, we had frequent floods that rose quickly and then would recede quickly, especially after major storm events. The past history on this site, from a disturbance standpoint, is probably a little bit different from our other ones that we discussed. Like I mentioned before, fire really did not have a role to play in the maintenance of these sites. We also, because these areas were rather narrow, the opportunity for conversion to different land uses like cropland and pasture land was really minimal. So this site has been sitting idle for over 80 years when the university took it over in the 1930s. So John now is going to talk about what's currently here and maybe some of the options we have to deal with managing this site. So John?
Very good. Thank you, Doug. Yeah, so as Doug mentioned, The species historically that were here are often many of the same species that we see today because the disturbance regime really hasn't changed that much. The primary driver is probably localized flooding and might take out a few trees on occasion, but that's probably the main disturbance agent. So the most common species in this kind of setting are going to be species like sycamore, black walnut, hackberry, various hickories like shellbark hickory, slippery elm, and sugar maple. As Doug mentioned, we do have a lot of upland species that occur in these well-drained bottomlands like this. We also have, in this particular site, a look-alike to sugar maple called black maple. And we'll give you a little view of what black maple looks like, but it's pretty common in this part of the Midwest, in lower slope positions, and in some of our well-drained floodplains, like here. I have a sugar maple leaf and a black maple leaf, just to show you the difference. So the black maple leaf is this one here. It's much broader. It's losing any kind of lobing at the bottom compared to the sugar maple, which has distinct lobes in it, including that basal lobe. There's a difference in size, and the black maple leaves have a tendency to droop on the edges. Our understory in this site has lots of Ohio buckeye. There's also lots of small diameter sugar maple that you'll see. And other places in this bottomland you might find pawpaw. Spice bush is another common species that you might find in this kind of setting. A species that really likes the high base saturation. In terms of oak regeneration, in terms of thinking about the future, these are not places that naturally accumulate a lot of oak regeneration. They're so mesic and lush. A lot of other species can occupy that understory and shade out any oaks that try to become established. Oaks are sometimes a component of these bottomlands, but they usually contain lots of other species anyway. So oaks are not a place we normally think of in some of these bottoms. They're just a minor component. In terms of productivity, these are very productive sites. We can have the capacity to produce really high quality walnut, veneer quality walnut of really high value if you're a private landowner. These would be the places that you'd want to manage for your walnut. Walnut is very common. We can show you some really nice ones here in the foot slope right adjacent to our floodplain. And, but very productive sites in terms of tree productivity, tree height, tree volume, and so forth. I think to talk a little bit about the future of these sites. These sites, like Doug mentioned, are very diverse naturally. These are probably places in the future where we can think about maintaining that biodiversity of species in our landscapes. Just by their position in the floodplain, they're in a position where they're receiving lots of water. They get also water from the nearby stream channel. So these are very mesic places where high water supply is usually prevalent throughout the year. And these are places that are going to be less susceptible to drought during dry periods, and can probably help maintain a lot of that species diversity, a lot of different species at that landscape scale. So I think for future management, these are hot spots for where to think about maintaining high biodiversity and managing for that specifically.
So John, I just have one other comment. I mentioned earlier that these sites are fairly flashy. They come up quickly but go down quickly. But in the future, with our climatic issues that are coming into play now, our storm events in this area, especially and across the country, are becoming more intense. And so we have extreme drought cycles, which could impact this site, but not as much. But when we have high rain events, we could have some significant damage from just stream flow in these areas and create open gaps, which may significantly change the structure and the composition on these sites. So that's just something to think about in the future. We can't control that because rain is rain. But that's something that sites like this, those issues may come into play in the future.
So we have made a stop, this is stop number 5, in an old field. So where Doug and I are standing now, back in the 1930s, used to be a pasture as best that we can tell. There are occasionally some large sugar maples and some other large trees that were left behind for shade in that pasture. But in 1939, that property, as Dr. Knapp explained about the Baskett area, was purchased by the federal government and leased to the university to do research. And so the vegetation on that site grew back into sort of a mid-successional forest that's developing here. It has a lot of we'll call field invader species that are taking over. But what we wanted to remind you of is the soils at this particular site are just like the soils that we saw in Site 1. In fact, Site 1 is just across the road, and we'll show you a picture of that soil just to remind you. But the soils at Site 1, if you recall, are the soil with the two very distinct loess layers separated by that band of silt coats. So we have those two different loess layers in that soil, pretty high water holding capacity, pretty good soil for not only growing trees, but also made a pretty decent pasture.
Like John mentioned, the soils on this site are very similar to the ones we first saw in the first stop right across the road. So you would typically then assume that we have, from a historic standpoint, a similar ecological site here, and we do. So looking at just the soils, we would classify this, if you remember, as a deep loess upland woodland. Remember, our woodlands were more open than our forest settings. It probably didn't have a mid-layer, but it had a fairly dense ground cover consisting primarily of prairie grasses, forbs, and shrubs. Now, John talked about the past here. One of the other things I want to point out, we probably assumed it was a pasture because right down the hillside here, there's a couple of ponds, which is another indication. And also one of the features that we see in this area, as these ridge tops kind of broaden, we tend to see more intensive agriculture. So in the past, this site was, like John mentioned, was cleared, converted maybe to cropland, but finally ending up as grassland with successional species now taking over.
And so presently here we have a lot of those field invaders that I mentioned. So the most common species that we've found in this area is eastern red cedar. You guys are probably familiar with seeing eastern red cedar in every fence row that you drive by in central Missouri. The birds disseminate the seeds, and so it's readily distributed. And it's a species that's really capable of colonizing old fields and harsh environments that are much harder for other trees to become established in. It is by far the most abundant species in these old fields out here at the Baskett area. But we also see some other species. There's American elm that you can find out here. There are remnant trees that were left behind, like some large sugar maples, like this individual I'm standing next to, that was probably left in that field for quite some time before it was left and forests have come back in. We also have lots of invasive species that come into this environment, like autumn olive, bush honeysuckle is common, and bittersweet is an invasive plant that we have here in the Baskett area in these old field areas. When we go into the native forest, we tend not to see those species, especially those invasive species, to the same extent as we do here in the old field setting.
So one of the problems on this site is the invasives that John talked about. Even if we left this idle for another 20 or 30 years, we could probably lose this understory to the invasives, especially the bush honeysuckle and the autumn olive. So from a management standpoint, that needs to be something that needs to be addressed immediately if you're going to do any site remediation here. So,
because of those invasive species preventing oaks and other natural vegetation to come back in, it's going to take a very, very long time in the absence of management before this forest would ever resemble the forest across the road, even though it's on the same soil. So this is a place where you could probably do some management to help speed that process along and restore some of those species. Probably some of the most important things that you could do here would just be controlling some of these invasive plants and removing them to allow some of the other native species to come back in. There is some oak advanced reproduction in this old field. And if you look around, you'll find some large oak seedlings around. There's also seedlings of ash, elm, there's some maples in here as well. So it's on its way to trying to develop that other forest, but because of these other problems associated with the invasive species, that's really going to slow it down.
So even in this present condition, this site does have some attributes that are good. It has wildlife cover. It has wildlife food, and also we've got a nice covering on the soil and a good strong canopy, and so it has good watershed protection too. So even if we don't do anything here, we'll still have those benefits on this site down the road. So.
The last thing that I wanted to do was call attention to a poster that Sarah Higgins has developed, and it's available for you to view here at the meeting, and a video of her talking about the results of that poster. Sarah is an undergraduate student at the University of Missouri. She's studying soils and environmental science at the university, and she's been doing a special project out here looking at some of the biological measures, and specifically the phospholipid fatty acids that are in the soil that we can extract from the soil and learn a little bit about them. And so in her poster, she describes some results out here that shows that even though this soil is the same as in Site 1, if she looks at the total phospholipid fatty acids occurring throughout the profile of that soil, this site actually has fewer total phospholipid fatty acids in the profile basis. But one thing that she noticed is that in the upper 5 centimeters of this soil, that there's a very high activity or high concentration of phospholipid fatty acids just in the very, very surface compared to the same soil in the forest condition. And that's a result that we think is associated with the availability of organic carbon in the surface of this soil. And that's largely a function of this early successional state of this forest and the fact that it's regrowing and generating a lot of carbon and biomass, especially in the mid and understory compared to that old growth condition. So I would invite you to have a look at some of Sarah's results in her poster and view her video to learn a little bit more in detail about what we're learning about some differences in the biological measures in our soils that are a function of not only the different types of soils that we have here at the Baskett area, but also the different past land use and that legacy of that land use and the influence it has on those soil properties. Well, we hope everyone has enjoyed this video of our virtual field trip. I can tell you as a research forester with the U.S. Forest Service, it's been a real privilege for me to work in this, this research center, this forest that we have here so close to the University of Missouri. And it's been a real privilege to work with my colleagues in the NRCS, especially related to the Soil Survey Division. So we hope that you've enjoyed learning a little bit about that, a little bit about our soils, a little bit about our forests and vegetation and our natural communities here in central Missouri.
Well, I'd like to just close with saying I hope you enjoyed our video tour. I know it's not the same as being on site, but at least we saved you two things. You didn't get tired going up and down all our steep slopes we have out here, and I guarantee you, unless you're sitting outside watching this, you didn't get any ticks or chiggers. So those are two great benefits from a virtual tour. So thank you again for viewing this video, and we hope you enjoy the rest of the conference.
Hi, my name is Sarah Higgins. I'm a student here at the University of Missouri in Columbia. I am in the School of Natural Resources. I'm entering my senior year, and I'm studying environmental science with an emphasis in soils. Last summer in 2019, I did a research project here as an undergraduate here at Baskett, looking at soil health parameters in areas with different historic land uses that are currently forested and comparing them on different soil types to see how they changed. While I was working on this undergrad research project, at the end I produced a poster to show these findings, which you'll be able to see. So with this project, our objective was mainly to look at soil health through measuring PLFAs, or phospholipid fatty acid analysis, to get a read on the biology occurring in these soils at different depths and down the profile. We also looked at total organic carbon and fungi and actinobacteria. So we sent those samples to the Mizzou Soil Health Assessment Center, where they were analyzed. So we had 12 plots we looked at, and they were all restoration plots here. They had two different types of soils mapped, Wellers and Bardleys, which you'll see here on this tour. So we had 3 plots for each mix of the land use. So we had 3 wellers in a forest, 3 wellers on a historically agricultural site, and then 3 barleys in a forested historic use site and 3 barleys in a historic agricultural use site. So the data we got back from that was really fascinating. We found that regardless of land use history, the barley soil type had more PLFAs, and that's just a rate of biological activity, so more biology, soil biology, inherently than the weller. And we also found that on the profile level, so the whole pit, the barley, the forested, historic forest land use had more soil biological activity than the agricultural historic land use. And however, in just the surface, so the 5 centimeters, the agricultural land use had more soil biological activity than the barley. Another really cool finding we found was the really strong correlation between total organic carbon in these soils and predicting the amount of PLFA that's also in the soils. So in regards to soil health, a lot of what you're finding can be determined by how much total organic carbon you have, and that could explain some of the other findings we found. So this is really cool information to enhance other research projects going on out here that can be used and also can be used in ecological restoration to help know what's going on in the soil. Hope you enjoy your virtual tour of Baskett. I enjoyed working here, so have fun diving into these soils.